Howdy! This is the second video of formation evaluation for organic rich shales, and I'm going to discuss and explain the well logs and petrophysical approaches for shale gas. However, it is important to mention that this is a paper review based on this publication that you can see here. The outline for this presentation is going to be first the definition of shale gas. Later, I'm going to explain key well logs, then the well logs response, subsequently shale gas reservoir identification methods, the key petrophysical parameters, and finally the main difficulties of formation evaluation. So I'm going to now define what is a shale gas. How I mentioned in the previous video, shale can be described as a sedimentary rock made of clay minerals and silt-sized particles with low porosity and low matrix permeability. The trapped gas in shale is often termed as shale gas and is mainly stored in the shale formation here, with two states of the absorbed gas, which is trapped mostly in the organic matter, and the free gas is stored in natural fractures. Now let's turn to the key well logs. The shale gas well logs are nearly the same as the conventional oil and gas reservoirs, including the conventional and special well logs. Some of the common problems include the type of rock and mineral, fluid identification, and rock mechanics parameters. The formation evaluation focus can be first shale gas reservoir identification and the potential hydrocarbon generation evaluation, such as shale gas reservoir classification, carriage recognition, or TOC estimation. Also lithology and reservoir parameters evaluation, such as minerals type, composition, porosity, gas content, or permeability. Also rock mechanics parameters, anisotropy and in-situ stress evaluation. For the first one, fracture identification, real-time monitoring, fracturing azimuth and fracturing effect, and finally real-time monitoring, horizontal well drilling and production process. Here we can see a table. This is a table of well logs and the petrophysical parameters available for shale gas. We notice NMR for TOC estimation, cross-dipole acoustic log used for gas content estimation, and gamma ray for mineral composition. The well logs response analysis for shale gas reservoir include lithology, physical, electrical, and gas-bearing properties, source rock, in-situ stress, and anisotropy, just to name some of them. For instance, we can distinguish gamma ray, which is all high, caliper, which usually expands, a high neutral response, low density due to gas content, and finally a mainly high resistivity. However, deep lateral resistivity and shallow lateral resistivity show medium or low value and negative separation in the shale reservoir. Now I'm going to explain shale gas reservoir identification methods. This is a figure that represents a conventional well log response of a shale gas in China, where we have porosity tracks here, gas logging, conventional logs, and finally gamma ray spectrum, just uranium, thorium, and potassium. Also, we can point out a normal caliper response, a high gamma ray in the shale layer with a high content of uranium and low thorium, a high TOC corresponding to high gas content, and a low density. Here's like where I describe most of the well logs responses. The key petrophysical parameters include the shale minerals composition. The minerals composition of shale can be measured by X-ray diffraction in the laboratory, reactivity logs that directly provide the minerals, and cross plots using combinations of conventional logs. Moreover, with these combinational logs, we can predict shale thickness. Here on the right, we have a figure of an X-ray radiograph and conventional well logs. For the second one, we have the TOC estimation. TOC is considered to be a crucial parameter for shale gas since it is closely related with kerogen content and types. In addition, it can be used to evaluate the hydrocarbon generation capacity. Several methods are used. The first one is a delta log R, which is the separation between the scale porosity curve and resistivity curve here. The second one is basically an empirical relationship with the density log and TOC from core analysis, which is the one here. Now I present maturity. The maturity is an essential index to evaluate the source. It can be obtained using well logs, specifically with resistivity and the combination methods of neutron logs and density logs. The formula of maturity is the one displayed here, and this is only effective for a layer of gas with a density porosity greater than 9% and a water saturation with greater than 25%. For porosity estimation is mainly calculated based on 3 porosity logs. It's important to mention that density porosity has relative high precision, so it can be used. The physical volume model is modified with TOC, it means just to include TOC, and it's given by both of these relationships for porosity and the density. And finally, the porosity can be estimated by the cross-plot correlation with the fitting relationship displayed in the graph. However, it is difficult to get a high precision porosity of shale because of the complex lithology and logging response. We have also gas saturation. High gas shale content corresponds to large resistivity reading. The gas content and TOC obtained by core analysis data can be also displayed a good correlation between them, where the gas content would be calculated with TOC. This is basically the TOC versus gas content plot, where each dot corresponds to the core analysis. Finally, rock mechanics parameters, which are extremely important for engineering operations in shale gas production. Cross-dipole logs can be used. They provide the slowness of compressional and shear waves to calculate the rock mechanics parameters such as Poisson ratio, shear modulus, and bulk modulus. Moreover, the in situ stress can be evaluated with well logs, with a combination of pore pressure analysis, image logs, and core analysis. Here on the right, we have a figure of ultrasonic image log. Finally, I'm going to mention the main difficulties of formation evaluation for shale gas. We know that the shale reservoir has the characteristics of low porosity and low permeability. So the log's response to log porosity and low permeability is complicated and not obvious, which is also one of the crucial difficulties of core information evaluations. The gas is mainly absorbed in the shale, so the log's response of the absorbed gas is complicated and less understanding. The lithology of shale reservoir is complicated and different from the conventional oil and gas reservoir. The well logs interpretation model is quite different from the conventionals. The well logs theory and models based on assumptions of linearity, homogeneity, isotropy, ideal elasticity is not completely suitable for shale gas reservoirs, so that needs to change. As shale is both self-source and reservoir, the trapped gas includes absorbed gas and free gas. The issue of how to identify the state and content of the absorbed gas is another problem. Thank you. These are the references used for this presentation.